What I'm going to tell you today really is sort of a numerical method, a numerical approach to trying to understand strongly correlated systems. And I understand I'm all keeping you from going to go see gorges, so I'll try not to run over here. So, and tomorrow I'll talk about sort of what I'm going to say is kind of variational plus, take the things we've learned today, the variational approach, and ask what steps we can go beyond them. And so what I'm going to do is I'm going to really talk about kind of a standard set of methodologies or sort of variational ansatz that people use to understand strongly correlated systems. And through that discussion, both today and tomorrow, of those variational ansatz, I'm going to mention a couple sort of bias selection of applications. And I'll point those out when we get there. But first, we really should ask ourselves the question, why is it we need to approach this problem in this way at all? Why can't we just use kind of methods that are better than variational methods that just kind of give us exact results? So I should say, my goal today is to make things largely understandable. So please stop me if you have questions. There's really, I know this stuff already. There's really no point in me droning on if people have questions. And if you have a question, I'm sure your neighbor does too. So let's start with something simple. Let's start with just asking ourselves why this is sort of necessary at all. And what we should appreciate is that classical physics is reasonably simple to simulate. In classical physics, the state is simple. You have a bunch of particles, and you specify the momentum and the position of them or something. And the state is simple, and moreover, the rules are largely local. You more or less have a local set of interactions, a local set of rules. You can emulate the gauge fields if you want. And you more or less can step everything incrementally. And so most things in classical physics have polynomial complexity to simulate. In fact, it was a long-standing sort of lore of computer science called the modified Church-Turing thesis that if it existed in the universe, you could simulate it in polynomial time on your MacBook. And so it turns out that classical physics, although there are lots of hard problems in it, everything can be simulated pretty easily. And everything is sort of prototypically, my laser pointer is dying here, prototypically kind of represented by these cellular automata. You have a bunch of pixels, you have a bunch of points, and you have some update rules that tells you to go to something else. So really, just to contrast that, quantum mechanics, quantum physics is really a fundamentally different beast. And there's both a good and bad side to that. The good side of that is that it looks like one of these days we'll be able to build quantum computers, and quantum computers will be able to calculate things that your MacBook can't. The bad side of that is that if you're interested in understanding the world, if you're interested in understanding quantum physics, things are hard because the simulations naively are of exponential complexity, which is to say that not only, well, for two reasons actually. To begin with, even storing the state directly is hard. I mean, if you want to write a quantum wave function out, at least at a naive point of view, it requires 2 to the n doubles, 2 to the n complex numbers. But moreover, the rule to update, right, is some big matrix, some 2 to the n by 2 to the n matrix. That's also sort of a rule that's going to cost you exponential time. And so really sort of fundamentally the problem here is that to get your hands on the explicit many-body wave function is difficult. And so now in quantum physics, there's a whole slew of approximation algorithms, of different techniques, of different methodologies that we have to use. And it all comes from the fact that doing things exactly, at least scaling to large systems, is difficult. So really, we should ask ourselves the question, what to do now? And so there are different answers to this question. I think throughout the week, you'll hear some different answers. You'll hear some lectures about DMFT from other people. The answer I'll tell you now is I'll say, look, one of the approaches that we can use is we can just go ahead and we can guess an answer. We have some many-body wave function we want. We're just going to guess a many-body wave function. And so what we're going to do is we're going to try to write down some answer, some guess for the many-body wave function that's compact and that's easy to work with. And what we'll see in the moment is that actually most things in Hilbert space are kind of irrelevant, and that in some ways helps us. And if you're going to play this game, if you're going to write down a guess, you better have some sort of way to arbitrate guesses, right? I mean, you and your friend both write down some guess. You better have some kind of heuristic to tell you whose guess is better. And so there are really two things that you might want to get right, and we'll talk about these both today. One is that there are some qualitative physics aspects that you want to get right. There are things like size consistency. There are things like you want to be able to capture the phases that you want to capture. I'll kind of point these out in detail in a minute, but you want to get the qualitative physics right. That's sort of your basic thing. But secondly, one of the very nice things about applying a variational approach is that there is an objective function, a heuristic, that tells you, when you have two wave functions, which one is probably better. And that objective function is the variational principle. It says if I write down a wave function, and if I guess the right one, I have some energy, and it's the exact energy. And if I guess the wrong one, it has a larger energy. And the fact that this happens is an advantage because it means I can write down many, many different wave functions. I can pick the one with the lowest energy, and that's a reasonable heuristic for quote unquote the best. Now, it's only a heuristic. You could imagine lots of other objective functions. You can imagine variances. You can imagine overlaps. You can imagine lots of things. This is the canonical thing that people use most of the time. Okay, and it turns out that this approach kind of sounds ridiculous at face value, right? Let's just guess what the answer is to the many-body wave function. This approach is sort of a long and venerated history, sort of in the study of quantum mechanics. I mean, BCS superconductivity, how was it solved? Well, Bardeen, Cooper, and Schrieffer more or less wrote down the BCS wave function and showed that it had the right physics properties. An understanding of quantum Hall, where did it come from? Well, in many ways, Laughlin wrote down sort of the right wave function and showed that it had the right properties. And so this is at least some motivation to think that the variational approach is really one that, although kind of at face value it sounds ridiculous, write down the answer to your problem, write down the many-body wave function, nonetheless might give you a lot of value if you can do it right. Now, there's sort of two kind of, let me say, fundamental problems or basic complaints with applying the variational approach that you'll hear over and over again if you happen to be doing variational approaches. So one of them is you might think, well, this is all well and good, but if you're not Bardeen or Laughlin, what in the world are you going to do? You need sort of deep insight, it seems, to apply this approach, because you need to be able to sort of write down, to guess the right answer. So that's kind of generic complaint number one. And generic complaint number two is that the variational approach really isn't a very useful one because it is biased. You more or less just get out what you put in. So you guess the right answer, and then you haven't really learned anything. Of course, there's a positive point of view on that complaint, which is that if you manage to do that, you sort of capture the right physics. And I think historically, these have been reasonable complaints to some extent. But I think as time goes on, these things that people have worried about for a long time have gotten less and less important. And I think they've gotten less and less important for two reasons. One is that we've gotten much more powerful optimization techniques to optimize wave functions, and these have come partially here from people like Cyrus, partially places like Trieste from Sandra Sorel and company. But these techniques have allowed us to optimize, instead of 2 or 3 parameters, tens of thousands of parameters. And being able to do that has allowed us to work with a much larger class of wave functions. And so if you're now optimizing 10,000 parameters, this concern that the world is biased is slightly less of a concern. The other advantage is, and we'll explore this a little bit today, is that we've really begun to sort of write down a large class of variational ansatz. And when you have many, many different types of ansatz, this means that you can go ahead and study many problems without having sort of great insight for a new variational subclass. Okay, can people still hear me? Can the recording still hear me? Okay, excellent. So what's going to be kind of the outline for the next 2 days? Well, the outline is really going to be a tour of the variational space. And as we tour the variational space, as we tour sort of different classes of variational ansatz, what we're going to do is we're going to sort of stop at 3 particular applications. So the first one is we're going to think about partons, and we're going to think about how we can use partons to understand phase diagrams with both topological and non-topological phases in it, bosonic phases, as well as compute things like critical exponents between them. So that'll be sort of our first kind of application stop. The second one is we're going to talk about an application of tensor networks to understand many-body localization. So when we get there sometime in the next half an hour, I'll tell you what many-body localization is, and I'll tell you how we've been able to use tensor networks to understand things. And then this is something I'll talk about tomorrow. We'll talk about how we've been able to use projector Monte Carlo, which is sort of an extension on variational Monte Carlo, to understand and simulate a bad metal phase. And so these are respectively done with my student Hassan, with my colleague David Pecker, and with Matthew Fisher and Katie Hyatt. OK, so are there any questions so far? Let me stop and make sure I haven't lost everyone already. All right, so before we get too far, let's just ask ourselves kind of a basic question. Let's ask ourselves, how big is Hilbert space? And Hilbert space is big, right? I mean, we have some wave function. Let's imagine it's on spins. And we need 2 to the n complex numbers to represent it. But the relevant part of Hilbert space, I mean, this is sort of a mathematical fiction, that Hilbert space. The relevant part of Hilbert space is much, much, much smaller. In fact, this is sort of a funny point I'm about to make. But even if you ask yourself the questions, how many wave functions can you describe in a short time? How many wave functions can you write a PRL about? There are only a very finite number, a very small number of wave functions that you can describe in 4 pages. The Hubbard model I can describe in 4 pages. Maybe I can't solve it, but I can at least describe it, right? I can say it's the ground state of this Hamiltonian. There are lots of things that I can describe in 4 pages, but the number of wave functions that exist is significantly, significantly larger than that. I can describe a wave function as the output of this quantum circuit. Now, that's something that I might not be able to do without a quantum computer, but it's at least something I can describe with sort of a short number of bits. I can write it down on a few pages of paper. But most of Hilbert space is not like that. Most of Hilbert space consists of wave functions that must be totally irrelevant, because we can't even write a paper about them. We can't even describe them in the universe. I assume only things we can write papers about are relevant, by the way. I mean, so it's the case that almost everything in Hilbert space is totally irrelevant in the universe. Yes?
Totally irrelevant to ground state properties?
No, period. There are many, many wave functions. Almost everything in Hilbert space you can't write, you can't even describe. So here's a non-ground state property. It's the 8 millionth excited state of the Hubbard model. Or it's the wave function I get by time evolving the Hubbard model as I turn on the interaction from t equals 0 to t equals 10, starting with a product state. I mean, these are all things that I've described very shortly to you. They'll fit in a PRL, that description. But nonetheless, most things in Hilbert space are too large to be described like that. And so almost everything in Hilbert space is irrelevant. Won't show up in the universe, can't be described in a paper, et cetera. I can't write a short computer program that will output it even if I run forever. Yep. Yeah, so that's a little bit more of a subtle point. So it's true that if you want to talk about some average over states or some disordered average, or I get to flip a bunch of coins, what I'm saying is not true. But at least the actual pure states that I can describe, the pure states that matter are very, very small. No. If I can describe it as a pure state as a quench, then it only lives in a very small fraction of Hilbert space. Because you can write down a description on how to get it. So there is some short description. So I think this is an underappreciated point. I mean, this is subtle, but it really means that almost everything in Hilbert space is totally irrelevant. And so it shouldn't surprise us that we might be able to do a better job of finding the important things, because almost everything is something that, I mean, doesn't show up, at least in any descriptable way, in the universe. OK, are there any more questions about that point? OK, so then what we care about is not, yes?
But a material knows all that, right? It can hold all that information.
It can, and the description, sure, the description, the ground state of Herbert Smithite is a short description. So that's something that I can write, I can describe. Most things I can't even describe in that way. Most things in Hilbert space I can't even say the words I can't even sort of describe as the ground state of Herbert Smithite. Yes. Yeah.
So given some state in the Hilbert space,
yes.
you're saying there is not a Hamiltonian there's not a local Hamiltonian for which that is a, say, excited state.
Yeah, I'm saying something even a little bit more general. If you pick a random state from the Hilbert space, there's no local Hamiltonian, there's no description, the ground state of XYZ material, there's no computer program that outputs it. It is completely undescribable. A random state in Hilbert space is a completely irrelevant part of the thing for physics.
Just making that statement based on kind of count.
Just a counting argument. There are too many states. Almost all of them are not describable.
Because it's a to the 2 to the.
That's right. Almost everything is irrelevant in Hilbert space. Yes.
Excuse me, I totally don't understand.
Okay.
I'm sorry, like, I understand when you say I can describe, but I don't understand it won't show up in the universe. Like,
Well, I guess it could show up in the universe and you just can't describe it. But
like that's I can live with.
okay, let's
Say it doesn't show up in the universe.
let's go with that for the moment. I think something slightly more powerful can be said, but for sake of argument, let's just say you can't write a paper even describing sort of the statement about almost everything in the Hilbert space.
But when you say something more powerful, what can you say?
Well, I think if it shows up in the universe, you can describe it as the thing that shows up in the universe at 10 to the minus 33 seconds, or 10 to the 33 seconds after the universe started. And that is a short description of that wave function. Okay. I think this is a true but subtle point, but let's not spend too much time on it. Let's sort of continue. So what we want is we want things that are not only compactly describable, but we also want things that we can efficiently simulate. And the sort of algorithm, the technique that for some of this lecture we'll use or talk about to sort of compactly, let me rephrase, to efficiently compute properties of that wave function is typically going to be variational Monte Carlo. My goal was to say something about variational Monte Carlo on the board, but I actually think I'm going to largely skip it. Variational Monte Carlo is sort of the method. It's a quantum Monte Carlo method. It's just typical Markov chain Monte Carlo. And what you do is you have a bunch of particles in some configuration and some basis. You change that basis a little bit, and you accept or reject based on the ratio of the wave function squared. People are free to ask me ad nauseum about variational Monte Carlo and the details of that algorithm afterwards, because most of the time I'm going to be talking about variational ansatz, sort of the qualitative wave functions in this talk. It's not central to it, other than it's sort of our go-to method for how we're going to compute efficiently observables and amplitudes. So what we want is we want something not only that's compactly representable, which is already a very small part of Hilbert space, but now we want to get our hands on things that we sort of have efficient access to observables about. So let's start someplace very simple. Let's start with free fermions. So in free fermions, you have some hopping, and the ground state wave function, which is the thing we'll talk most about today. The ground state wave function is the product of a spin up and a spin down determinant. And just to be pedantic, what I mean is a wave function is something that eats locations of the electrons and spits back a number. The electrons fill up a matrix. That matrix is generated by having a bunch of single particle orbitals. Those single particle orbitals are three-dimensional functions. They eat the location of the jth particle. For the ith single particle orbital, that gives you the location of the Mij matrix elements, and then you take the determinant of it. Okay, I won't be so pedantic for the rest of the thing, but let's at least start everyone on the same sort of page. And I'll be sloppy. Sometimes I'll write the determinant of one matrix, where implicitly I'll mean the determinant of a spin-up matrix times the determinant of a spin-down matrix. All right, good. So this is the ground state wave function of free fermions, and it's not only compact, but it also, we can compute things with it quickly. It's computing a determinant. As an interesting aside, free bosons has a very similar structure. Instead of determinants, you should have permanents. And for those who don't know, a permanent and determinant are the same things, except for you replace all the minuses with pluses. And it turns out that although determinants are very easy to calculate, permanents are not very easy to calculate. Permanents require exponential amount of work to calculate. So this is an example of something that's very nice to sort of compactly represent. And it's a very pretty formula, but it's one that often we can't do anything about, at least for big system sizes. OK, that's an aside. So now what should we do? So we have our answer for the non-interacting case. And now we're stuck. We're going to turn on interactions. We no longer can solve it exactly. So now we have to do something approximate. And there are sort of two paths forward sort of on our journey. One of them is we're just going to begin dialing in sort of more qualitative physics. That's what I'll talk about today. What I'll mention a little bit at the beginning tomorrow is that there are sort of systematic expansions, ways where you can start with some wave function and bootstrap to some better wave function. But let's start with just sort of dialing in kind of the right qualitative physics. We have a free fermion product of Slater determinants. And now what we're going to do is we're going to add interaction. And we should ask ourselves the question, what's missing? Well, what's missing from this wave function is that the upspins, the downspins are not talking to each other. They don't know each other exists. They don't see each other. And so there's some correlation that's missing. Your upspins and downspins can sit on top of each other, et cetera. And so what we should do if we want to clean up this wave function, if we want to make it better, is we should dial in some piece of the wave function that keeps the upspins and downspins apart. Okay. And that is typically called a Jaster factor. It's typically written like e to the minus u of, say, Ri and Rj. And typically we would choose that, for example, if we have a repulsive interaction, like one does for electrons, to keep the electrons apart. And in fact, one could say more generally, we had this wave function u, and we wrote that as a two-body term, u of Ri, Rj. But one can expand further. One can write u of Ri, J, Rk, Rl, et cetera, et cetera. Three-body terms, four-body terms, et cetera. One can have arbitrary bosonic correlations. And so one could write that as e to the minus big U. Question, yes?
Just a simple question.
Yes.
It's obvious that you put exponential here to suppress something you don't want.
Yes.
Something you want. But does it have to be exponential? Or it could be any other function that has a similar effect?
You could put anything you want there. The exponential is typically the thing you do with Jaster factors. The other reason you do this is you like to make a distinction here, which is what I'm about to make, that you want to think about writing the wave function as sort of a fermionic piece and a bosonic piece. And by writing this as an exponential, this forces this to be strictly positive. And so it's a reasonable bosonic thing. It's a reasonable bosonic ground state. I mean, it's a wave function. You can write anything in the world you want there. And that's legal to do. This is sort of the standard thing to do. This is a Slater-Jastrow. And the reason is because it is fruitful qualitatively to think of this as a fermionic piece times a bosonic piece. Anything else? Any other questions? Sorry, Eric, I wasn't paying attention to when I started. When is the?
So probably if you aim to end at 10:02.
OK, great. OK, so now that we have sort of this next step, what we're going to do is we're going to ask ourselves the question, is this Slater-Jastrow form capturing some of the qualitative physics that we want to capture? And this will sort of dovetail us into one of the applications that I was talking about. So there are two qualitative things that I like to consider. One of them is the following. We have a fermionic piece times a bosonic piece. We'd like to ask ourselves the question, can this bosonic piece capture the different bosonic wave functions that we care about? The qualitative aspects. Can it even give us the right phases? OK, if we use big U, if we expand to all orders, of course it can give us the right phases. It can give us anything. Let's ask a slightly more refined question. If we just have a short-range two-body Jastrow, can the bosonic piece even give us the qualitative right phases that we might want?
Sorry, Bryan.
Yes?
Why did you say that? I mean, the nodes are determined by the fermionic piece. Right?
That's right. So what I'm asking is I'm asking in variational Monte Carlo, can you write even all of the qualitative bosonic phases that you care about with a two-body short-range Jastrow? This is a perfectly good question.
Okay, but I'm not sure what you mean by bosonic phase, because you have a phase for the entire system.
That's right. So we're just going to consider the bosonic piece. Nope. Nope. I'm going to do something strange. I'm just going to say, look, I want this general approach to be powerful. I'm going to use for the bosonic piece e to the minus u sub 2. And I'd like to know what kind of phases e to the minus u sub 2 can capture.
So you're asking a question now about bosons?
I'm asking for part of this only a question about bosons.
For me, when you part, you allow any split.
For the moment, yes. And it's, OK, go ahead.
But just fixing the fermionic piece to determinant mean that you somehow fix the nodes of the wave function?
If I pick a particular determinant, I will fix the nodes of the wave function. That's correct. Okay, and the second qualitative question I'll ask, is this wave function as a whole size consistent? Okay, one can ask lots of qualitative questions. There's a reason I'm asking these two. Yes, Andre?
Do you allow for your u to be a log?
Yeah, I'll allow the u to be a log. Well, let me rephrase. When I talk about short range, I'll not. And yes, if you allow the u to be a log, you'll be able to represent other qualitative phases that you can't with just a short range. I'll say that again in a second. Yes?
So you have split the Fermion function into this Fermion piece and Bosonic piece.
Yes.
So it just means like the Fermion piece can give you a minus sign when you change something.
That's what it means. The bosonic piece can't.
Yes, but can I also understand I can have even piece of this fermionic piece to become, I mean, in total I can separate the wave function into odd number of fermions.
Yeah, I can do all of these things. So I should say, I am charting a path through the space of variational ansatz. It's a very particular path that I've chosen. There are lots of paths one can take, and part of the reason I've chosen this path is because it stops by the applications that I want to tell you about. But there are lots of other options. Okay, so let me tell you about the first question. Let's just stare at the bosonic piece and ask, can it capture the qualitative phases that I care about? What are the qualitative bosonic phases? Well, there's mod insulators, there's superfluids, there's, I don't know, fractional turn insulators, all sorts of things. Let's just pay attention to a mod insulator. One of the very basic things of our bosonic piece is we'd like to be able to write down a mod insulator, right? It's a basic bosonic phase. And what I'm going to tell you now is that if I just give you the variational ability to have short-range two-body Jastros, you can't write down a mod insulator. So let me just tell you that why. I mean, I've just told you it, but let me tell you why. So what is a mod insulator? A mod insulator has the property that it is not superfluid. Okay? Let me ask the following question. Let's consider this variational wave function, two-body Jastro. And what does it mean to be not superfluid? It means that if I look at the one-body real space reduced density matrix for two particles, I and j, for two spatial locations, I and j that are very far apart, those go to 0, i.e. I don't have a Bose condensate. This is the real space version of saying I don't have a Bose condensate. And what you'll see is that if I have a short-range Jastro and I destroy a particle over here and I create it over here, there's some cost to doing that, but there's not an infinite cost to doing that. That wave function, that amplitude, that probability doesn't go to 0. And so any short-range two-body Jastro will always have a Bose condensate, will always be a superfluid. And therefore, is not a very good representation of a mod insulator. Now, Andre asked, suppose, can you use log Jastros that go as a log? Yeah, if you use, there is a solution to this, pushed by Frederica Becca and Sandra Sorella and company, where they have largely divergent Jastros, and that will solve this problem. I will describe in a minute what I believe to be a more aesthetic solution to this problem. Yes?
So I guess to calculate any correlation functions, you basically have, that's like correlation functions of some classical StatMech problem.
Yeah, that's right. That's in fact all variational Monte Carlo is.
But classical StatMech problems can go through phase transitions?
No. Okay, good. Sorry, let me be a little bit more careful. The classical partition function course of a StatMech problem corresponds to the diagonal part of the wave function. And so for the diagonal part of the wave function, you can get anything that you can get classically. And yes, it goes through phase transitions. But the off-diagonal piece is a little bit more subtle. It's not just a classical partition function. And this is off-diagonal along range order. This is a fundamentally quantum effect. All right, so that's condensate. One can say the same thing about size consistency. Size consistency is a property that is good to have in a wave function. What is our class, a manifold of wave functions? What is the property? The property is the following. If I use my wave function to represent system A and I have an energy EA, I use my wave function to represent system B and have an energy EB. If I use my same class of wave functions to represent both systems, and they were very far apart and don't talk to each other, I would like to have EA plus EB. Seems like a basic property that I'd like to have of a class of wave functions that I'm using. And short-range Jastros can't ensure size consistency. And you can read this in detail, but the short reason is that in order for this to happen, I want to fix n particles over there and n particles over here, and there's nothing that prevents sort of charge fluctuations. There's nothing that prevents n plus 1 particles living over here if I have a short-range Jastro. It's sort of the same problem there was with the condensate fraction. There's nothing that prevents sort of charge fluctuation way beyond what it should be allowed. So short-range Jastros are nice. Slater Jastros, they're sort of the standard for lots of quantum Monte Carlo techniques, but they do sort of fail on these two qualitative aspects. OK, again, there is a solution to this which requires sort of using which requires using second quantized Jastros. This goes by lots of names. It gets invented over a few years. In fact, it gets invented at Cornell every few years. Anyway, it goes by lots of names. And you can use that to sort of patch up this problem, but you have to use really high-order Jastros still to patch up the problem. OK, so here's what I propose is a prettier way to patch up this problem. So this is inspired by a parton construction from Mason and John McGreevy. And OK, there's a whole other way I can tell this story starting from some of the slave fermion work of Mason and company. But I have chosen to tell the story this way today. So what we're going to use is we're going to do sort of a parton decomposition. So what does a parton decomposition do? Well, it says, look, I have a boson, and I'm going to pretend I'm going to fractionalize it into 2 fermions. And then what I'm going to do is I'm going to glue them back together. And one way of gluing them back together sort of analytically is to use a gauge field. If you're a numerics person, the way you glue them back together is you tell your variational Monte Carlo that these 2 fermions are actually stuck at the same spot. So this is much like what was being talked about in the previous lecture, where you had a bunch of fermions and they were sort of glued in a bag. We're going to do the same thing here. And it turns out that you can write down, sort of inspired by the field theory, you can write down wave functions that represent these sort of states. And what are the wave functions? Well, there are 2 determinants. These determinants come from non-interacting Hamiltonians. The non-interacting Hamiltonian is here. It's not important. What is a little bit important is that this non-interacting Hamiltonian has different Chern numbers. But at the end of the day, you have a product of 2 non-interacting ground states of 2 non-interacting Hamiltonians that are glued together. And then you can just ask an empirical question. You can ask the question, as I tune around in this parameter space, can I get the bosonic phases that I care about? Can I get a mod insulator, a fractional Chern insulator, a superfluid, et cetera? The answer is yes. So because we just talked about superfluidity, I'll just point it out. This here is the condensate fraction. Notice this is in K space. This is what everyone looks for a BEC. There's a macroscopic occupation of the K equals 0 component. And as you tune around this variational subspace, you can empty out that condensate fraction. And this is really actually pretty impressive because lots of very natural things that you might write down, like a Slater Jastro with a 2-body Jastro, can't do this. Moreover, this wave function has the property that it is also size consistent. So it's size consistent almost for a trivial reason. So a Hartree-Fock state, a single Slater determinant, is size consistent. It's size consistent because more or less I can lock half my particles in system A and half my particles in system B by just choosing the right single particle orbitals. Now, if I have the product of 2 determinants, I can do exactly the same thing. I can essentially, on each determinant, lock half my particles to system A and half my particles to system B. So it turns out that this, for free, gives you many of the properties, sort of qualitative properties of a variational wave function for representing bosonic phases that you might want, this parton decomposition. And then you can ask, what physics can you do with this thing? OK, you have a bunch of wave functions. Who cares? Well, let me just tell you 2 things that are really nice. So one of the bread and butter of people who do sort of spin liquids and topological phases and all sorts of things is they like to scan phase diagrams to decide what phases are where. And people will do this all the time with variational Monte Carlo. And one of the problems with doing this is often your variational Monte Carlo wave function for sort of an ordered phase is just much better than your variational Monte Carlo wave function for some crazy exotic phase. And so more or less you're comparing apples and oranges. And here we have a nice uniform wave function, a product of 2 determinants that represents almost everything in this space. And so we're no longer as badly comparing apples and oranges. And so here we have some Hamiltonian that we've dreamed up as essentially a Hubbard model, a Bose-Hubbard model with hardcore interactions, with a frustrating next nearest neighbor hopping. One can write this as a magnetic field so it doesn't look quite so pathological. And then one can map out the variational phase diagram, and one gets superfluids and fractional turn insulators and Mott insulators and all kinds of nice things. So that's one thing one can do. The other thing that's really nice about this framework is that before, if you wanted to tune yourself to a critical point, that was kind of a painful thing to do because you had some type of wave function for phase A and a totally different type of wave function for phase B. And now, as you want to tune yourself to a critical point in this framework, you just have a product of two determinants, and you go from phase A to phase B as you tune the determinant. And so there's a beautiful wave function right for the critical point. Because there's a beautiful wave function right for the critical point, you can go ahead and you can measure critical exponents associated with transitions between anything you want. Yes, Andre?
There's a wave function for what?
There's a wave function for every phase.
So you start off with some complicated Hamiltonian, you're trying to find the wave function. And then you
Right, so I have a class of wave functions. Yes. Variationally. So I have the Hamiltonian that I'm trying to solve, and I have this wave function, which is the product of two determinants.
The part-on construction, the part-on wave function, the non-interacting wave function that then you kind of put. How do you find the parameters in the part-on wave function?
You use variational Monte Carlo.
So the parameters.
Yeah, well, no, there are two of them there.
Well, in general,
Yeah, but we can optimize tens of thousands now.
okay, so that
I mean, here we just optimized these two for this particular example, but we can optimize tens of thousands, so that's not a fundamental problem.
So what is your Monte insulator break any symmetry? It's obviously not what I call a Monte insulator. It's not a vanilla Monte insulator, so to say. It's something very exotic.
Well, I don't know that it's something very exotic. I think it's a vanilla Mott insulator. It's built in a weird way. It's built as a product of these non-interacting sort of turn insulating determinants, but
How do you know? How do
I mean,
you,
it
how
looks
do
like
you
a-
define your phases?
So-
something that has two Fermi surfaces of some fractionalized product.
it does, yeah, but if you measure your observables, it looks largely like a bread and butter Mott
You're
insulator.
measuring only equal time observables, right?
Well, we're measuring superfluid fractions, and yeah, but we're only measuring equal time observables. But if I have a wave function, it's the only thing I can do. I mean, I don't have access to them.
Gap state with where the quasi-particles are bosonic. There's nothing.
How do you know that?
You can. I mean, there's a field theory from which motivates this part-on construction and analyze that field theory. And show that it's completely.
Well, I don't know. You got two. Oh, you're taking diamond Fermi surfaces?
No, so those two determinants are just churn insulators. So they're both band insulators. You're just projecting two band insulators.
Okay.
I mean, I can imagine that for gap states, but like in general, like think of, I mean, that's got only two parameters.
Yes.
You chose like a parameter. I could choose next nearest neighbor.
Right, I could parameterize this by all of the single particle orbitals. That's right.
But you're saying the strategy is just optimize over.
Yeah, it's not what we've done here, but a perfectly valid and typical strategy is I write all of the parameters, I parameterize all three-dimensional functions, there are n of them, and I just optimize everything. And we've done that. I mean, other people in the room have also done that, but we've done that for all sorts of spin liquid candidate systems. Is we've optimized over every single, to zeroth order is equivalent to optimizing over every single hopping and every single pairing function.
So, okay, I mean, maybe.
What if you do determinate on
Uh,
Would your phase diagram be different?
Well, certainly if you use a different version of Monte Carlo, it may or may not be the same or different.
This is a boson problem. You should be able to just do.
No, there's, no, on one line you can, this one axis. Yeah, that's not possible because there's a sign problem. You can do it here, and people have done it here, and this transition is about right. So the variational phases are about right, where you can do an exact quantum Monte Carlo, but the rest of this diagram can't be done exactly. We're going back, and we're doing it with DMRG and ED and all sorts of things. And this is at least roughly right. We're not sure if it's exactly right or not yet.
So then if you did it for r equal to 0.
Yeah, this can be done exactly.
Yeah, so
And this transition point.
There you have a Mott insulator phase.
Hmm?
Your Mott insulator phase that your wave function is capturing.
Yeah.
And there is a Mott insulator phase that you get with a determinant like Carlo.
Well, some version of Monte Carlo, yes.
Oh, yeah.
But yes, fine.
Yeah,
That's right.
Non-variation,
Yes.
right? So how do you know whether the two approaches are describing the same minus later phase? I think it differs with
Yeah, so we could compute fidelities, we could compute overlaps, but we haven't yet. We know that this transition point is about right. We know that this looks like a vanilla mod insulator, but we have not done a careful study in the sense that we haven't computed overlaps and things yet. But we could. There's nothing fundamentally that proves.
vanilla mod insulator. How are you looking at?
Well, for example, if we look at the structure factor, we see appropriate peaks and things. So that's the kind of thing that we want. Equal time things. Yeah, that's all we have access to here.
So do you see indeterminates change suddenly as you go on phase transition?
There's a pretty sharp change. I mean, it's not a formal jump. There's some chain. What?
And to determine what its fractional choice is, you calculate the many-body churn number?
We calculate the many-body churn number, as well as the topological degeneracy. Yeah.
At the phase boundary, at the critical point, your gap's vanishing, right?
Presumably, but of course, we just have a wave function, so all we can do is we can measure things.
Right. You can measure energies. You have your
Yeah, but we don't have excitations. So we can look at decay of correlation functions, and I think that
only measure the ground.
we only measure. We're writing down a guess for the wave function.
Yes.
All right.
So you have evidence of this. So in high C base, people were like doing variation on the flux state, etc.
Yeah. Yes.
With skeptical degrees of success.
Yes.
The proof is more successful.
Well, I don't know what that means exactly. We have a variational thing. We've done it using reasonable wave functions that are sort of apples to apples, and we're going back and we're using bigger hammers to try to verify whether or not this is really right or not. Okay. Other questions?
Did we say something about those exponents?
No. I'll say something to you afterwards about those exponents. I mean, some of these are predicted for the first time ever. Some of these are things that the superfluid mod insulator, this is about right. This is large, the anomalous exponent here. On the other hand, no one, for reasons I don't understand, has predicted this or computed this numerically for hardcore bosons yet, even though one can do it exactly, or at least I can't find it in the literature. I'll say more about it to you in prison. Okay. I agree. Surely somebody's done it. I can't. So whoever knows where it is in the literature, just tell me so that I can compare.
Well, we know the answer.
Okay.
Your single particle.
The answer is 0.03.
Yeah, so it's anomalously high. I agree. I don't know what's going on there yet.
The single particle Hamiltonian does the phase transitions also.
Yes. Okay, good. Other questions? Okay, so now let me go to part 2 of today's talk. So far I've sort of taken you in a path starting from free fermions and sort of cleaning it up in some qualitative way. Now let me just start from a different starting point. So if you're lost or fallen asleep, this is a good time to sort of tune back in, because this is really starting from the ground up again. So there's another class of variational ansatz called matrix product states or tensor network states. And I'm going to describe those, or at least some sliver about those, so that I can tell you something interesting about many-body localization. Okay, so this is primarily a one-dimensional ansatz. It is biased, just like any variational ansatz is, toward low entanglement. And the way it works is the following. What is a wave function? A wave function is something that eats configurations and spits back a number. And so the rule here for how it eats configurations, spits back the number, is for each, let's just consider spin up or down. For each site, the spin is either up or down. For each site, there are 2 matrices. If the spin is up, I take the up matrix. If here the spin is up, I take the up matrix again. If here the spin is down, I take the down matrix. I multiply the matrices and I take the trace. Great, I have now described to you some prescription, some rule for how I give you a configuration up, up, down, and how you get back out a number. And that's enough, right? That describes what a wave function is. That wave function is called the matrix product state. That is the wave function that DMRG spits out at the end of the day, although that fact was not appreciated for many years, although has been known now for a couple decades. That's what it is. And there's an interesting theorem from Matt Hastings. Theorem says that in one dimension, if you have a gap local Hamiltonian, it is well represented by a matrix product state. Good. So that's at least one reason why matrix product states might be reasonable things to do, particularly in 1 dimensions. And one can ask the question, how do we find them? And you could use variational Monte Carlo. People have done that. But actually, these are very matrixy. And so there are linear algebra techniques that allow you to find them faster. OK, there's 2 techniques, actually. I'm not going to tell you either of them. But this one is really nice because it is an exact algorithm. So in variational Monte Carlo and everything else, almost always, when you're optimizing things, you can get stuck in local minima. And it turns out that there exists a not very practical, but nonetheless exact algorithm to find the ground state of a matrix product state. And this has just been known in the last maybe year by people, Amish Vazirani and company. It's a beautiful algorithm. I don't have time to tell you, but if you want to ask me afterwards, I'll tell you because I like it a lot. And it's sort of amazing that there exists an algorithm that really finds the true ground state. What that means, the implication of this is for 1D gap local Hamiltonians, there exists an algorithm that always guarantees to find you the true ground state. And that's pretty awesome. OK, so there it is. There's the picture of the algorithm. I'm not going to tell you. Good. I intended to tell you, but I didn't. I'm running late. Good. So now we're going to talk about many-body localization, and we're going to sort of extend the ideas of these matrix product states. So many-body localization is a very interesting field of physics that has a lot of people working on it. This is a very old list. There are like 5 times this number of works at this point. And what is many-body localization? It's essentially the interacting analog of Anderson insulators. So in Anderson insulator, you have non-interacting system, and you have disorder. And then all of your wave functions become exponentially localized. And now there's a very perfectly reasonable question to ask. What happens when you turn on interactions? In fact, if you read Anderson's paper, this is the question he asked. And he said, oh, that's too hard. I'll just turn off the interactions and solve that problem. And that's probably got the same answer. Anyway, people have been very interested in trying to better understand this problem. So let's talk about sort of a concrete microscopic example. You have some Hamiltonian Heisenberg model plus a magnetic field. And that magnetic field is sampled from, is disordered. It's a quenched disordered magnetic field sampled from some top hat distribution. Good. What is the phenomenology of the many-body localized phase? Well, the key thing is that there is no conductivity at finite temperature, even at infinite temperature. Typically, even if I have an insulator and I turn on temperature, it conducts. There's some exponentially attenuated conduction. And that doesn't happen in the many-body localized phase. It's really, really, honest to goodness, truly 0. OK. In addition to that fact, there's a failure of statistical mechanics. When you go to StatMech 101, what do they tell you? Day 1, and they say, you know what? You have some big system, and that big system acts as a heat bath for little chunks of it. And it turns out that if I happen to be in a many-body localized phase, statistical mechanics breaks down. The big system does not act as a local heat bath, as a big heat bath for the rest of the system. Those are sort of the key things. There's no level repulsion of the eigenstates. So typically you have level repulsion of the eigenstates, and that doesn't happen here. The eigenstates are also pathological in that they obey an area law. There's localization kind of in Hilbert space. The other key thing is that there are sort of conserved integrals of motion. So many of you probably know things about Bethe ansatz and sort of integrable models. And this is sort of an emergently integrable model. It's a model where there are lots of local conserved integrals of motion, but they show up in a whole phase, and they show up in an emergent way. And that's pretty cool. All right, so it doesn't thermalize. You can probably guess what that means. It means if I look at a small chunk of a pure quantum system, a small chunk of my big system, and I measure something like the reduced density matrix, a thermalized system is thermal. It's rho thermal at some energy density. A non-thermalized system is not thermal. For the experts in the room, the fact that this doesn't obey a volume law, that the eigenstates obey an area law, means that you can't possibly thermalize. OK, we can talk about what thermalizes, but it's not important at the moment. The eigenstates are weird. The eigenstates have abnormally low entanglement entropy. I already told you this. Let's get to the variational ansatz part of the story here. So here's the game. What I'd like to do is I'd like to sort of describe the many-body localized phase variationally. Okay, now, many-body localization is a dynamic phase transition, which is to say the important thing is not the ground state. It's not the finite temperature density matrix. Actually, that's nonsense because it doesn't thermalize. The important things are the eigenstates. And so what I'd like to have is I'd like to have a variational representation of the eigenstates. In fact, I want a variational representation of all of them, of all 2 to the n eigenstates. And so that's somehow the game here. So what is the kind of spirit of the thing that I want? Well, the spirit of the thing that I want is as follows. Imagine this totally crazy pathological example. I have a Hamiltonian with no interaction and just a magnetic field. Okay? Quenched disordered magnetic field. Then you know what the ground state is. All the spins point in the direction of the magnetic field. And you know what the excitations are. You choose some of these spins and you flip them. If I want another excitation, I choose some more spins and I flip them. And so we'd like to be able to tell a story like this about many-body localization, where there's actually interactions on. It's not this pathologically simple thing, but a story that sounds kind of like this. OK, that's going to be the game for the next 7 minutes. Although Eric just left, so maybe I get to talk forever. OK, Una has not yet left. If I scare Una away, then I can continue talking. OK, good. So let me just tell you the answer, and then I'm going to step back and tell you how we used the idea of variational wave functions to come to that answer. So the answer is the following. So I described for you, so this is the Hamiltonian I care about. It has interaction. And I described to you what a matrix product state is. So there is a matrix product state for the ground state. I have 2 matrices for every site. Now it turns out that there is, OK, so these are the A matrices. These are the matrices for the ground state. There's also a set of matrices, let's call them the B matrices. And all of the excited states are represented by all combinatorial combinations of A and B matrices. So if I want an excited state, site 1 I'll pick an A matrix, and site 2 I'll pick a B, and site 3A, and site 4A, and site 5A. If I want another excited state, site 1 maybe B, site 2B, site 3A, site 4B, site 5A. Okay. This has generated the entire spectrum of eigenstates. So this is kind of amazing, by the way. What this means is all 2 to the n excited states are generated by essentially 4n matrices. Okay, there's no reason. I mean, we understand now why this is, but a priori, there's no reason to expect you should ever be able to do this for anything. I mean, typically you think, I need 2 to the n numbers to describe every excited state, and there are 2 to the n excited states. And now, in a very small number of numbers, 4n matrices, each which happen to be of finite size, I can describe all the excited states. Yes, Andre?
Why would that be an excited state? Why would the excited state not be, your first one plus whatever B on site 5?
I'm about to tell you. Or I'm about to try to tell you. OK, other questions? Yes. Yes. No, they're not. And they're not the same, largely because this is a disordered system. So the matrix on site 1 and the matrix on site 2 and the matrices on site 3 are different. So you really need 4 matrices per site, 2 for spin up and spin down for A, 2 for spin up and spin down for B. So it really is 4n matrices that are required here. I'm sorry? Good question. It doesn't grow with system size. There's a slight lie there. I'll show you a plot where we measure it. To zeroth order, it doesn't grow with system size. The slight lie is we're doing a disordered average, and of course, it might be that there is some disordered realization that's not really disordered. You got the answer 0 the whole time, and then you're back to kind of the non-disordered case. There's a Griffiths effect problem. Don't worry about it. Up to that slight lie, it's constant bond dimension. Good. Yes.
Sorry.
Absolutely.
Are you saying that's true for that Hamiltonian?
Yes.
Or any Hamiltonian?
No. I'm saying this is true for this Hamiltonian where W is strong enough. More generally, I'm saying it's true for any Hamiltonian in this many-body localized phase. So there's a specific type of phase called the many-body localized phase. And for any Hamiltonian in that phase, this is true. Actually, as a slightly more subtle statement, this is always true as long as you're willing to let the matrices grow to be arbitrarily system-sized. As long as the matrices can grow as a function of system size, it's always true. Well, there are 4n matrices for the whole spectrum, but then the matrices get big as the system gets big, and so that's not so useful. That will come out of what I'm about to tell you. Other questions? I'm about to break my microphone again. OK, so how do I know this? I have to tell you one more sort of fact about matrix product things. So this is a matrix product operator. It represents, instead of a matrix product state represents a vector. Matrix product operator represents like a Hamiltonian, a matrix, an operator, a unitary matrix. What is a Hamiltonian? It is something that eats a bra and a cat and spits out a number. So for each sigma 1 and alpha 1, there is a matrix. 4 matrices per site. It's a matrix product operator. Okay, good. Moreover, I have to tell you how you multiply a matrix product state by a matrix product operator. So if I multiply a vector by a matrix, I get a vector back. So this is a matrix product state. And I just have to tell you how I get that matrix product state. And so that matrix product state is actually the matrix in the operator times the matrix and outer product with the matrix in the state. Okay, this is just a rule. It turns out to be the right rule. It's not at all clear why it's the right rule. This is the rule for the moment. If you're an expert in matrix product operators, this is the rule you know and love. If you open Shulwalk's review article on matrix product states, this is the rule you'll read. This is how you generate a matrix product state when you multiply a matrix product state by a matrix product operator. For each of the matrices, you take an appropriate outer product. Okay, so now the limiting case, the case where you multiply a matrix product operator by a product state is very simple. A product state is a matrix product state with bond dimension 1. Its matrices of size 1 by 1. So this is a product state, 1, 0, 0. That's the matrix. It's a 1 by 1 matrix. If I multiply a product state by a matrix product operator, all that happens is it pulls out some of the matrices from the matrix product operator. The outer product of the scalar 1 with a matrix is a matrix. 1 outer product A is A. Okay. So now I have just told you some interesting properties about matrix product things. And now I'm going to tell you why the statement I've been making is true. So we know that there is some unitary operator that diagonalizes that Hamiltonian. That's just a statement. And if we think for one moment about what a unitary operator that diagonalizes a Hamiltonian is, it is a matrix that eats product states and spits back eigenstates. So 10 seconds of thought will convince you of that fact. So now let us consider what happens when we take the matrix product operator representation of U and we apply it to a product state. It will spit back an eigenstate. And if you think about what I've just told you, I've told you that a product state applied to a matrix product operator just pulls out some of the matrices in the matrix product operator. And so if I stick in all 2 to the n product states and apply the matrix product operator representation of U, that will give me all 2 to the n eigenstates. And all 2 to the n eigenstates that I get out will be of this form where it's just going to pull out some of the 4n matrices that are living inside that matrix product operator. Okay, and I've said nothing at all yet about many-body localized phases. This is the statement that the statement up to this point is true for all eigenstates, for all Hamiltonians. All eigenstates can be. For all eigenstates, for all Hamiltonians, this is true. Now, what you should care about is you should care about how big these matrices get, because that's sort of what I've shoved under the rug. And so now we're going to ask an empirical question. We're just going to go numerically measure. We have some physical arguments, but let's just ask an empirical question. Let's measure how big those matrices are in the many-body localized phase. There's a technical detail that I won't say anything about, other than the unitary matrix that I hand you has a gauge freedom. You can permute which product states correspond to which operator, which eigenstates. Moreover, you can permute the phases of each state in the unitary matrix. If you ever diagonalized anything in your life, you know that this can be a kind of a bane of your existence if you're like computing Berry phases and things. There's a little bit of gauge freedom to the unitary matrix. You have to be careful to choose the right gauge freedom or you'll get garbage. Okay, if you choose the right gauge freedom and you don't get garbage, you can measure as a function of chain length whether in the many-body localized phase the bond dimension saturates. And okay, this is what this graph shows. What it shows is if you have strong enough disorder, as a function of chain length, the bond dimension saturates. And there's a lot hiding in this graph over here. In particular, you can actually see the mobility edge. So if you're used to thinking about Anderson insulators have a mobility edge. And you can actually sort of read off the mobility edge from this graph. But I don't have time to tell you that at the moment. But if you're interested, come ask me. But as an empirical numerical statement, there is a saturation of the bond dimension in many-body localized phase as the system gets large. OK, so I will say 20 more seconds of something. This gives you a variational ansatz for the many-body localized phase. And then all of this phenomenology of the many-body localized phase that I told you 10 minutes ago can more or less be read off of just knowing this information. Things like the fact that their area law eigenstates are totally trivial. But even things like the local integrals of motion. Here is a local integral of motion. If I take u, and then I take sigma z on site 2, u dagger, that produces a integral of motion. That's a trivial statement. It's actually true for all eigenstates, for all Hamiltonians. And then, because it is in this representation of a matrix product state, you can read off that it's local, because it only differs from the identity on one site. And matrix product states are AKLT-like. They decay exponentially. So that's all I'm going to say. Right, that's all I'm going to say at the moment. So sort of as a conclusion, I've sort of told you about some very interesting variational ansatz. I've told you sort of 2 stories, 2 physical applications. Next time I'll talk about sort of bad metal phases and projector Monte Carlo. Sorry, I'm a few minutes over.
Questions?
U is the matrix that diagonalizes the Hamiltonian. So if you're working with a small system and you just want to sort of give a proof of principle, you just diagonalize it. You choose the right gauge freedom, which is a royal pain in the neck and took us a long time, and that gives it to you. If you want to do it for a very big system, you have to sort of do some kind of variational optimization in the spirit of variational Monte Carlo. There are a number of groups, myself included, who are working on that and either have papers are out or about to have papers out about that.
Yes. What do you mean by the right gauge freedom? What makes the others bad?
Good. So what makes the others bad is the following. So in these many-body localized phase, what you want to do is you want to preserve locality. So imagine that you start with the ground state. Let's say all zeros map to the ground state. And then I flip this 1 to 1. You don't want sort of the relevant quasi-particle in the eigenstate to show up over here. So if you imagine there are sort of relevant quasi-particles that are localized in the eigenstates, if you flip 0 to 1 here, you want sort of the relevant quasi-particle to flip over here. And you can just do this by choosing the right mapping of eigenstates to product states. But you can also choose a wrong mapping, and things will be a disaster. Great.
How about going in the reverse direction? Does the existence, so we know, it's believed that there exists this universal Hamiltonian for many-body localized phases, just some commuting terms, local commuting terms.
Yes.
And that's kind of true for big interaction strength. So can one use that information to show that this matrix U has a local?
Yeah, good question. So there is a complementary paper by Geoffrey Vidal, Anusha, and company that says not quite what you're asking for, but something at least similar in spirit, which is that if you have conserved integrals of motion and they are compact, which is not actually true, but is close to true, then there exists a local unitary of this form. So that's not what you want, but it's something in the spirit of what you want. I don't know the exact answer to your question. Well, 1, they're not truly compact, and 2, the existence of the Hamiltonian you're talking about doesn't guarantee that those are integrals of motion, but it's almost what you want. Maybe it's what you want, I don't know, but it's at least very close.
So in the first part, you talked about this phase diagram.
Yes. 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 So we're doing it. It's hard to do because the phase diagram we're talking about is 2-dimensional. Matrix product states are best for 1-dimensional things. But you can still do it, and we're doing it, and we have preliminary results that I'd be happy to talk to you about privately, but we don't have sort of the definitive answer yet. Yeah, the zeroth order intuition is that, there are 2 intuitions. One is that a matrix product state is a product of matrices. That's a linear thing. And so now you have to map the 2D world into some linear thing. The second intuition is that essentially 2 sites that are next to each other are actually far apart on your 1D linear thing. And so there's a huge amount of entanglement in the real world. You've got to transfer that huge amount of entanglement over a huge distance in the matrix product state.
Okay, well, Bryan, one last question.
So normally, when you're asked the spectrum, you're asked to give an eigenstate for some energy.
Yes.
Now this spectrum is exponentially dense.
Yes.
And I assume that that matrix B, I got lost again, but assuming the matrix B is obtained correctly, if you've acted once or twice, okay, and if you acted 100 times, those are, or in very different spots, those states are actually not very close to each other in energy. Those sort of states close to each other in energy are very far apart.
Are far apart with respect to the structure of the MPS. That is a correct statement.
So you can generate the states, but to actually compute their energy, to actually, if I ask you for a state at some energy, you wouldn't be able to give it.
Right. This framework is not very good for that. We have a separate, almost done paper with a separate suite of algorithms that will do what you want, but doing it exactly in this framework is hard.
Okay, with that, let's thank Bryan and all the lecturers.